Tomorrow night at 21:23 Coordinated Universal Time, a rock the size of an office building is going to skim past Earth at 57,000 miles, inside the orbit of the Moon, closer than the satellites that broadcast your television. The news has been calling it stealth, approached stealthily, hidden by solar glare. They are wrong, every one of them, and the truth they got wrong is the smaller half of a much bigger story. Because there really is a stealth zone. There really is a half of the sky we cannot see, and the rocks that come from it have already hit us, more than once, without warning, and the system being built to fix that will not fly for another 16 months. Tonight, we're going to look at every word the news got right, the ones they got wrong, and the ones they simply haven't said about this unusually close flyby. If you find this kind of investigative breakdown valuable, hit the like button and subscribe to the Sky Lab, and drop a comment with where you're watching from and whether you'll be looking up at Monday night's flyby. Now, let's get into it. Part 1. The rock they saw 8 days out. On May 10th, 2026, just before 5 in the morning, a robotic telescope at the top of Mount Lemmon in southern Arizona caught a faint point of light moving against the stars. The exposure time was seconds. The point of light was magnitude 21, which is to say it was at the bleeding edge of what the telescope can see. A first image, a second image, a third image, and the software flagged the motion. By the time the data were uploaded to the Minor Planet Center and a designation was issued, the object had a name, 2026 JH2, and the orbital solver had a result that made the operator pause. 8 days, 16 hours, and the object would skim Earth at 0.237 lunar distances, inside the orbit of the Moon, closer than any geostationary satellite, about 57,000 miles from the surface of our planet. The size, given how faint it was at how far away, somewhere between 15 and 35 meters across, about the same size as the rock that exploded over Chelyabinsk, Russia, in February of 2013. For the next 2 days, observatories at Stewart, at Farpoint in Kansas, and at Magdalena Ridge in New Mexico chased follow-up astrometry. The orbital arc grew from a few hours to 2 days. The missed distance held. The condition code, which is how astronomers express the uncertainty in an orbit, stayed at 9 out of 9, maximum uncertainty. Not because the rock was unusual, because the observation window was short and the object was small. By Tuesday, May 12th, the formal announcement went out as Minor Planet Electronic Circular 2026-J84. By Thursday, Fox Weather had a tweet pinned at the top of their feed, close to home. By Friday, every cable news anchor with a green screen graphics package had run the same 45-second story. Asteroid, recently discovered, extremely close approach, Monday, May 18th, 21:23 Coordinated Universal Time, plus or minus 6 hours, 16 minutes, 91,000 kilometers, 0.24 lunar distances, no danger to Earth. The story was accurate. The framing was misleading. Every word the news got right, and they got the headline wrong. Because here is what almost every piece of mainstream coverage of JH2 said, sometimes in those exact words: stealthy, approached stealthily, discovered late, hidden by the sun, outshone by solar glare, caught by surprise. The Daily Galaxy ran it, Universe Magazine ran it, IFL Science ran it. The implication was, this rock crept up on us from a region of the sky we cannot see, and it could just as easily have hit us. 8 days warning was framed as evidence of a system that almost failed. That implication is wrong. The geometry says otherwise. When Mount Lemmon detected JH2, the asteroid was at a declination of about plus 31 degrees. That puts it in the northern celestial hemisphere, near Ursa Major, well separated from the Sun, which in mid-May sits near declination plus 19 degrees in the constellation Taurus. The angular separation between the asteroid and the Sun at discovery, what astronomers call the solar elongation, was nowhere near the Sun glare zone. JH2 was found at night, from the night side of the sky, by a ground-based optical telescope that cannot operate any other way. Its post-discovery sky track shows it moving from north to south, crossing the celestial equator on the day of closest approach itself. That is the trajectory of an outbound object, observed from the night side, as Earth catches up to it on the inside of its orbit. JH2 did not stealth. JH2 was not hidden in solar glare. JH2 is, by every metric astronomers use, a normal Apollo-class near-Earth asteroid found in a normal way at a normal solar elongation by a normal ground-based survey. Why then was the warning only 8 days? Because the rock is small. When you point a telescope at a faint point of light, the brightness you measure is the sunlight that point reflects. The reflected sunlight scales as the inverse square of the distance from you to the object. It also scales with the cube of the object's radius, because that is roughly how surface area changes with size. Put those two scalings together, and a 5-meter asteroid is visible only when it is within about 100,000 kilometers of Earth. A 20-meter asteroid like JH2 becomes visible when it is within about 10 million kilometers. A 1-kilometer asteroid is visible from across the inner solar system. So when JH2 showed up in the Mount Lemmon data at magnitude 21, 8 days out from closest approach, it was doing exactly what a 20-meter rock does. It was invisible until it was close enough for the reflected sunlight to rise above the detection threshold of the telescope. Then it was visible. Then it was characterized. Then it was published. 8 days. Not because anything failed. Because the rock is the size that gives you 8 days. If JH2 had been 4 meters across, we would have caught it 20 hours before closest approach. If it had been 1 meter, we would have caught it 3 hours before. If it had been a kilometer, we would have known about it for 10 years. The warning time does not measure how good our defenses are. It measures the size of the rock, and in the case of JH2, the size of the rock is somewhere between a school bus and an office building. This is the first thing the news will not tell you. The warning time is not a story about luck. It is a story about geometry. But the second thing the news will not tell you is bigger than the first, and it is true. Yes, there is a region of the sky where ground-based optical telescopes are blind. Yes, that region hides some of the most dangerous incoming asteroids we will ever face. Yes, a Kelebintz-class rock came out of that region in February of 2013, and zero warning reached the ground, and 1,500 people were hurt by flying glass. Yes, another rock came out of a similar geometry over Akron, Ohio, on March 17th of this year, and we did not see it coming, and the only reason no one was hurt is that the airburst was small and was high. The blind spot is real. The concern attached to JH2 by Fox Weather is real. It just does not apply to JH2. The news got the right concern attached to the wrong rock. So in this video, we are going to do something the news did not do. We are going to take the concern that mainstream coverage raised, and we are going to attach it to the rocks where it actually belongs. We are going to walk through the half of the sky that Earth cannot see, and we are going to look at why we cannot see it. We're going to look at the missions being built to fix that, the funding fights they survived, and the gap years before they fly. We are going to look at the asteroids in the catalogue right now that have a non-zero probability of hitting Earth in the coming centuries, and we are going to look at how the system rates them. We're going to look at the 11 asteroids that humans have predicted before they actually hit, including the one that hit 3 days ago in the Arafura Sea between Australia and Papua New Guinea that almost no one outside the planetary defence community noticed. And we're going to ask a question at the end that the news did not ask. If the system that gave us 8 days of warning on JH2 is the system we trust to keep us safe, what do we do about the geometry where that system cannot see at all? Because Monday's flyby is the visible kind of asteroid, there is another kind. And that is the kind we need to talk about. But before we go there, let's stay with JH2 a moment longer. Because the rock itself, even normal as it is, has things worth knowing. The orbit is an Apollo-class trajectory, which means the semi-major axis is greater than 1 astronomical unit, and the orbit crosses Earth's. Specifically, JH2 has a semi-major axis of 2.43 astronomical units, an eccentricity of 0.585, an inclination of just 6 degrees from the ecliptic, and a perihelion at 1.01 astronomical units. That last number is what makes the classification borderline. 1.01 is right on the boundary between Apollo and Amor. JPL classifies it Apollo. The Minor Planet Center lists it as AMA. The discrepancy reflects the short observation arc. With more data, one of the two will lock in. The aphelion stretches out to 3.85 astronomical units, which means at the far end of its orbit JH2 reaches nearly to Jupiter. The orbital period is 3.77 years, so this is a rock that spends most of its time out beyond Mars and only briefly dips into the inner solar system, where it can occasionally encounter Earth. The Earth minimum orbit intersection distance, The closest the orbits can possibly come is 0.0007 astronomical units, about 105,000 kilometers. The Monday flyby will not be as close as the MOID allows. It will be closer, 91,300 kilometers, plus or minus 4,500. The relative velocity at closest approach is 9.17 kilometers per second, about 33,000 kilometers per hour, slow as near-Earth objects go. The slow speed is also why the orbital deflection from Earth's gravity will not be enormous. JH2 will leave its current orbit, but it will not be flung into a wildly different trajectory. According to the Sky Lab Ephemeris service, the next 10 years contain no close approach to Earth as close as this Monday's. The rock will return to the inner solar system on its 3.77-year cycle, but the geometry will not align for another close pass anytime soon. The Virtual Telescope project, run by Gianluca Massi from his observatory in Italy, will host a live online observation feed starting at 1945 Coordinated Universal Time on May 18th, about 1 hour 38 minutes before geocentric closest approach. The asteroid will be near peak apparent magnitude of 11.5 by then, visible in a 6-inch or larger amateur telescope from a dark sky site. From the northern hemisphere, observers will be looking at it in the constellations near Leo as it crosses the equator. From the southern hemisphere, observers will catch it at the higher declinations as it streaks south after the encounter. And there is one more piece of context for JH2 worth pinning down before we move on. The rock is not alone this week. JH2 is part of a cluster. On May 12th, asteroid 2026 JM2 passed Earth at about 0.1 lunar distances, about 38,000 kilometers, smaller than JH2, around 3 to 7 meters, but closer. On May 14th, just before the close of business Pacific time, 2026 JV3 passed at 0.13 lunar distances, about 50,000 kilometers, 2 to 4.5 meters across, and then on May 15th, at 1344 Coordinated Universal Time, asteroid 2026 JN4 did not miss. It hit. Atmospheric entry over the Arafura Sea between Australia and Papua New Guinea, less than 1.5 meters across, about a meter, give or take half a meter, detected from a short observation arc by the European Space Agency's Meerkat Impact Monitoring System and NASA's Scout system, and flagged as a high probability impactor in the final hours before entry. 2026 JN4 is the 12th asteroid in history that humans have detected in space, predicted to hit Earth, and then watched hit Earth. The 12th, 3 days before JH2 will not hit. The cluster pattern is real. It is also, however, partly an observational artifact. Twilight surveys, Atlas expansion, the systematic improvement in detection algorithms, they are catching smaller and closer rocks more often. The rocks are not arriving more often. We are seeing more of what was always passing through. The cluster of 4 sub-lunar distance events in 5 days is a milestone for our detection capability, not a signal of a swarm. The honest framing is, this is what the asteroid environment around Earth looks like all the time. We are just finally seeing it. But again, that framing applies only to the part of the sky we can see. The rocks that come in from the part of the sky we cannot see do not show up in the cluster. They do not show up at all. Until they arrive, and that is where we go next. Part 2, the half of the sky that is closed. Let me ask you a question that, when you first hear it, sounds like a riddle. Why can you not see the stars during the day? The honest answer is not that the stars are not there. They are. The honest answer is that the daytime sky is too bright. The sun, 93 million miles away, illuminates the atmosphere from above. The molecules of nitrogen and oxygen scatter blue light in all directions, which is why the sky is blue. The total brightness of the daytime sky is roughly 10 million times brighter than the brightness of the sky on a moonless night at a dark observatory site. Roughly 10 to the 7th. The faintest star you can see with your naked eye on a clear, dark night has a surface brightness that, against the daytime sky, would be utterly drowned out. This is not just a sentimental observation about why we look up at night and not at noon. It is the operational fact that defines half of Earth's defense against incoming asteroids. A ground-based optical telescope works by collecting photons. The asteroid emits, or rather reflects, photons from sunlight. The telescope's job is to detect those photons against the background photons of the sky. If the background is dark, even a faint asteroid stands out. If the background is bright, the asteroid is lost. There is a threshold. Practical asteroid surveys can operate when the solar elongation, the angle from the Sun to the target, is greater than about 50 to 60 degrees. Less than that, and the scattered solar flux washes out the faint moving point. Inside about 50 degrees of the Sun's position in the sky, the telescope is blind. Half the sky, give or take, falls inside that 50-degree cone at any given time. Some of the inner part of that cone is permanently closed. Some of it opens up briefly during the 20 minutes of astronomical twilight, when the Sun is below the horizon but the sky is still glowing. Surveys like the Zwicky Transient Facility at Palomar in California, the Asteroid Terrestrial Impact Last Alert System, telescopes in Hawaii and Chile, and the Schmidt Telescope at Pisca Stato in Hungary push observations into that twilight window with 30-second exposures. They can reach down to about 30 degrees solar elongation when conditions are right. But inside 30 degrees, it is closed, not because of policy, not because of choice, because the photons are not there to collect against a background that bright. Now consider the orbits of certain asteroids. Most near-Earth asteroids are Apollo class. Apollos have orbits that cross Earth's, but they spend most of their time outside Earth's orbit. From our perspective, an Apollo asteroid spends most of its time visible from the night side of the sky, in the anti-solar direction. We can see them, we can track them. JH2 is one. The 11 predicted impactors of the past 18 years were almost all Apollos. The system works for Apollos. Then there are Atens. Atens have semi-major axes less than 1 astronomical unit, but they still cross Earth's orbit. They spend more time inside Earth's orbit than outside. They are harder to see than Apollos because they are more often in the sunward direction relative to Earth. But they do swing out to the night side occasionally, and we catch them when they do. Then there are Asteroids. Asteroids, also called Apoeles, are asteroids whose entire orbits are inside Earth's orbit. Their aphelion, the farthest point from the Sun, is less than 0.983 astronomical units. They never come out to the night side from Earth's perspective. Their maximum solar elongation from us is about 75 degrees if their aphelion is right at the boundary, less for smaller orbits, down to about 45 degrees for the smallest. They live perpetually inside the daylight blind zone, with brief twilight windows offering glimpses. As of October 2025, the entire catalogue of known Asteroids numbered around 39 objects. 2019 astronomers had identified one named Asteroid. Today there are 2 named, 9 numbered, the rest with provisional designations. 7 of them are flagged as potentially hazardous. The first one was identified back in 2003 by the LINEAR survey, and we are still finding them, slowly 1 or 2 per year, in twilight images. Then there are Asteroids. Asteroids have aphelion less than 0.718 astronomical units. Their entire orbit fits inside the orbit of Venus. They never approach the Earth's night side, ever. The maximum solar elongation we can ever see them at is even smaller than for an Asteroid. We have currently identified exactly one Asteroid. Its name is Alochaxnim. It was discovered in 2020 by Wing-Huan Ip and his team using the Twilight program at the Zwicky Transient Facility. 1 out of an estimated population of hundreds to thousands. This is what the daytime sky is hiding. The Asteroids and Asteroids are largely unknown. Some of them are small, some of them are not. Granvik and colleagues in 2018 modelled the expected population. Their estimate suggests roughly 1,800 to 2,500 Asteroids with absolute magnitude H less than 22, which corresponds to diameters of roughly 150 metres and larger. Of those 1,800 to 2,500 large Asteroids, we have catalogued at most about 40. 40. That means there are roughly 50 large Asteroid-class asteroids that we have never seen, never measured, never characterized, for everyone we know about. Most are not on impact trajectories. Some, statistically, must come close. Some, on multi-century timescales, must impact. We will not know which. We cannot see them. This is the blind spot. This is what the news raised by accident with the JH2 coverage, even though JH2 itself is not from this region. The blind spot exists. The blind spot is closed, and from the blind spot, we have already been hit. The most famous case is Chelyabinsk. On the morning of February 15, 2013, at 20 minutes past 9 local time, a fireball brighter than the sun crossed the sky over the southern Urals in Russia. It was first reported by drivers on their morning commute who saw a streak of light, then a contrail, then a shock wave that arrived 2 minutes later and shattered windows across an area the size of New Jersey. The fireball entered the atmosphere at 19 kilometers per second, at a shallow angle of 15 to 20 degrees from the horizontal, and broke apart at about 30 kilometers altitude in an airburst with the energy of 400 to 500 kilotons of TNT, the Brown et al. Paper in Nature later that year titled a 500 kiloton airburst over Chelyabinsk and an enhanced hazard from small impactors, pegged the parent asteroid at about 17 to 20 meters across, with a mass of 12 to 13,000 metric tons. 1,500 people were injured, mostly by flying glass from windows blown out by the shockwave. 7,200 buildings were damaged. 6 cities took the brunt of it. There was no warning, none. No telescope on Earth saw it coming. The first time any human being knew the rock was there was when it appeared in the morning sky as a fireball. Why? Because the rock came in from inside 15 degrees of the sun. The angular distance from the sun to the radiant, the point in the sky the meteor appeared to come from, was, to use the Borovica et al. Companion paper's measurement, just inside the daylight blind zone. The parent asteroid was an Apollo with perihelion well inside Earth's orbit. On its inbound leg toward the impact, it was travelling almost directly toward the sun from Earth's perspective. There was no time, no geometry, and no telescope that could have seen it. The Chelyabinsk rock was, in size, somewhere between JH2 and a typical city block, 18 meters across, bigger than the rock that detonated over Tunguska, Siberia in 1908 by perhaps a factor of 10 in mass, smaller than the regional disaster class, small enough that it did not destroy anything outright, just shattered glass and burned the optic nerves of a few hundred people who looked directly at the fireball. Big enough that 1,500 people went to the hospital. If you want to know what the half of the sky blind spot can do, Chelyabinsk is the answer. 18 meters, 0 warning, 1,500 injuries, and we are still here because the rock was small and the airburst was high. The next one of that size that comes in from that geometry will arrive the same way Chelyabinsk did. We will see it when it gets bright in the morning sky. We will hear about it when the news arrives. And it is not a hypothetical that the blind spot is still active. The geometry has not changed. Earth still moves around the sun still lights the daytime sky. A Tiras still cannot be observed from the ground. There has been no Chelyabinsk class repeat in the 13 years since, but there has been a smaller reminder, a much smaller one. On the morning of March 17th, 2026, at 57 minutes past 8 Eastern Daylight Time, a fireball entered the atmosphere in broad daylight over Valley City, Ohio, about 30 miles southwest of Cleveland. The rock was approximately 6 feet across, around 1 3/4 meters in diameter, with a mass of about 7 metric tons. It airburst at roughly 30 miles altitude, about 48 kilometers, with an energy equivalent to about 250 tons of TNT. Not a regional disaster, not a glass-shattering shockwave at ground level, but a daylight fireball in spring over a region of 10 million people, visible from the District of Columbia to Indiana to North Carolina to southern Ontario. The American Meteor Society logged 175 eyewitness reports across 14 states and 1 Canadian province. The Ohio bolide was 3 orders of magnitude smaller than Chelyabinsk in mass, 3 orders of magnitude, but it came from a similar geometry, a near sunward radiant, and like Chelyabinsk, no telescope on Earth detected it before it arrived. None. The rock was simply too small, and it came in from the wrong side. The Fireball Season blog at NASA acknowledged it. The Watchers analysis at Watchers.news connected it to a Q1 elevated fireball cluster across the Americas. The CNEOS fireball database logged it. 250 tons from the sunward direction 8 weeks ago over a populated American state. No warning. If the Ohio rock had been 20 times bigger, it would have been Chelyabinsk. If it had been 40 times bigger, it would have been a city killer. We would have learned about it the same way after. This is the answer to the question that the JH2 coverage was accidentally raising. The half of the sky we cannot see is real. The hits have already come from it. The hits will continue to come from it. The only question is when and how big and where. Part 3. The light we are about to switch on. If you cannot detect an asteroid because the sky behind it is too bright, you have 2 basic options. You can move the telescope, or you can change the wavelength. The first option is what NASA is doing. It is called NEO Surveyor. The full name is Near Earth Object Surveyor. The current launch date is no earlier than September 2027, aboard a SpaceX Falcon 9 from Cape Canaveral. The spacecraft will be inserted into a halo orbit around the Sun-Earth Lagrange 1 point. L1. That is a point in space about 1 million miles toward the Sun from Earth, where the gravitational pulls of the Sun and Earth combine with the centripetal force of orbital motion to create a stable position. A spacecraft parked at L1 moves with Earth around the Sun, but from there it has a view of the entire sky, including the half of the sky that, from Earth's surface, is washed out by daylight. That is the first part of the fix. Move the telescope off Earth's surface, away from the atmosphere, away from the geometry that requires the Sun to be behind you to see a faint object in front of you. The second part of the fix is the wavelength. NEO Surveyor will not use visible light, it will use infrared, specifically 2 bands. The first runs from 4 to 5.2 microns, the second runs from 6 to 10 microns. Both are well outside the visible range, well into the thermal infrared. Why infrared? Because asteroids in the inner solar system are warm, the Sun heats them. Their surfaces sit at temperatures of 250 to 300 Kelvin, roughly minus 23 degrees Celsius. Anything at that temperature emits thermal radiation. The wavelength of the peak emission for objects in that temperature range falls right in the 6 to 10 micron band. So a 6 to 10 micron infrared telescope detects an asteroid by its own emitted heat, not by reflected sunlight. That single decision, to look in the thermal infrared rather than in visible light, collapses the blind spot. An asteroid hidden in solar glare from a ground-based optical telescope is still emitting thermal infrared photons. Those photons travel just fine. The infrared sky background, especially from L1, is dark. The Sun's overwhelming visible light dominance, which drowns out reflected sunlight asteroids in the daytime sky, does not extend to the same degree into the thermal infrared. So NEO Surveyor can look at the sky within 45 degrees of the Sun and still see asteroids. The NEO Surveyor telescope itself is small by space telescope standards. A 50 centimetre aperture, about 20 inches. Compare that to the 18-foot mirror on the James Webb Space Telescope, or the 7-foot Hubble. NEO Surveyor is the size of a backyard amateur telescope. It does not need to be bigger because its job is not to image distant galaxies. Its job is to detect bright thermal sources in the inner solar system, scanning continuously, building a catalogue. For that mission, a 50 centimetre passively cooled infrared scope at L1 is enough. The mission's top requirement, the one that justified the program in budget hearings, is to detect and catalogue at least 2/3 of all near-Earth objects 140 metres in diameter or larger within a 5-year baseline survey. 140 metres is the size threshold for what NASA calls a potentially hazardous asteroid. An asteroid that big, if it hit Earth, would not destroy a continent. It would destroy a region. It would do to a city what the Tunguska airburst in 1908 did to 900 square miles of Siberian forest, except concentrated in an urban area. The Congressional George E. Brown Jr. Near-Earth Object Survey Act, which Congress passed in 2005, mandated that NASA find 90% of these objects. As of 2024, the survey was only about 40% complete. The remaining 60% live, statistically, in the parts of the sky we cannot see well from the ground, either smaller tens that we miss because they spend too much time sunward, or Arcturus and Vettiris that we cannot see at all. NEO Surveyor exists to find them. The mission has been a fight. It started life in 2005 as an idea called NEO-CAM, which was proposed by Amy Mainzer, then at the Jet Propulsion Laboratory, now at UCLA. The proposal went through round after round of Discovery-class mission selection. It was descoped, it was deprioritized, it was waitlisted. In 2017, NASA designated it as a Mission Directorate priority and renamed it NEO Surveyor. In 2022, the White House budget proposal cut more than $130 million from the project and proposed delaying the launch by 2 years or more. NASA rescinded $33 million of the $143 million that Congress had already appropriated for fiscal 2022. What happened next is one of those stories that almost nobody outside the planetary defense community remembers. The Planetary Society wrote a letter, the National Space Society co-signed it, the science community filed comments, and then Congress in the December 2022 Omnibus Spending Bill and again in the CHIPS and Science Act explicitly intervened. The CHIPS and Science Act included a provision barring NASA from cutting NEO surveyor funding to cover cost overruns on other missions. The Omnibus mandated at least $90 million for the mission. The House added another $55 million. The Senate added $40 million. The launch is back on track. Critical design review was passed on February 11, 2025. The spacecraft bus is in testing at BAE Systems Space and Mission Systems in Boulder, Colorado, which used to be Ball Aerospace before the corporate rebranding. The total mission lifecycle cost is roughly $1.2 billion. For comparison, the James Webb Space Telescope cost about $10 billion. The Hubble Space Telescope, when adjusted for inflation, cost about $16 billion. Mars Sample Return is currently projected at $11 billion. A mission whose purpose is to detect a class of objects that have hit the planet within living memory, that have killed people within historical record, that exist in numbers we cannot currently measure, comes in at about 1/10 the cost of Mars Sample Return. The reason it took 22 years from concept to launch is not that the science was hard. The reason is that the funding was hard. Planetary defense has historically competed poorly against astrophysics and Mars exploration in NASA's discretionary budget. It is winning now, finally, partly because of Chelyabinsk and partly because of the political reality that a congressionally mandated survey of 140-meter objects requires hardware, and that hardware is now built, and that hardware needs to fly. September 2027, 16 months from today. That is when the sunward blind spot starts closing, at least for the bigger objects, at least at infrared wavelengths. But NEO Surveyor is not alone. The European Space Agency is building a complementary mission with a different focus. It is called NEO-MIR, Near-Earth Object Mission in Infrared. The launch is targeted for the early 2030s, no earlier than 2030. The orbit is also L1, between Earth and the Sun. The telescope is also infrared, with 2 channels covering 5 to 10 microns. The aperture is also small, about half a meter, comparable to NEO Surveyor. But the mission scope is different. NEO-MIR is designed specifically to detect Chelyabinsk-class objects coming in from the sunward direction, with at least 3 weeks of warning. The worst-case scenario, where an object is detected only as it passes near the spacecraft itself, still gives 3 days of warning. Compare that to the 0 warning that Chelyabinsk gave in 2013. Compare it to the 8 days that JH2 gave for a target that was not even from that geometry. NEO-MIR is the early warning system for the rocks that come from the wrong direction. The European Space Agency's own description of the mission on the official mission page is striking in its honesty. The opening paragraph says, and I quote, "From Earth we are blind to asteroids near the Sun as they are outshone by its glare. ESA's planned NEO-MIR mission will be located between Earth and the Sun and will act as an early warning system for asteroids 20 meters and larger that cannot be seen from the ground. 20 meters, Chelyabinsk class, from the sunward direction, 3 weeks warning. That is the gap NEO-MIR is built to close, and the European Space Agency, on its own 2024 YR4 explainer page said, and again I quote, "It was not detected sooner because it approached Earth from the day side of the planet, from a region of the sky hidden by the bright light of the sun. That was about 2024 YR4, the rock that nearly hit Torino 3 earlier this year." The European Space Agency, in plain language on its own mission page, has acknowledged that the sunward blind spot is a hole in Earth's planetary defences, and that ESA's job is to fix it. There are also partial ground-based workarounds. The Zwicky Transient Facility at Palomar in California runs a twilight survey program developed by Wing Huen Ip, Kwanzi Ye, Bryce Bolin, and Frank Mashi. 30-second R-band exposures during the 20-minute astronomical twilight windows at dusk and dawn. The program runs every clear night. Since 2019, it has found 1 Vatira, the famous Alochaxnim, 4 Atiras, 6 long-period comets, and 2 short-period comets. The Bolin et al. Paper in Icarus in 2025, titled The Palomar Twilight Survey of Alochaxnim, Atiras and Comets, is the public scientific output. The Shepherd team at the Cerro Tololo Inter-American Observatory in Chile runs a similar twilight program using the DCAM camera on the Blanco 4-meter telescope. They found 2021 PH27, then the shortest period asteroid known, with perihelion at 0.13 astronomical units, well inside Mercury's orbit. They found 2025 SC79 in September of last year, also fast orbiting. The Atlas telescopes in Hawaii and Chile operate routinely into twilight. Pan-STARRS pushes deep on twilight observations as well. These programs are pushing the edge of the blind spot inward, down from 60 degrees to 30 degrees solar elongation. But inside 30 degrees it remains closed, with no ground-based fix available. That is where the space-based infrared missions take over, so the situation right now, in May 2026, is this. The ground-based optical surveys are catching everything outside about 30 degrees of the Sun, and they are catching it down to magnitudes that correspond to objects a few meters across when those objects are very close. They are working as designed. The twilight surveys are extending that to 20 or 30 degrees. The space-based infrared mission to close the rest of the gap, NEO Surveyor, launches in 16 months. The European complement, NEO-MIR, launches 4 or 5 years after that. Until then, the sunward sky between 0 and 30 degrees solar elongation is closed. That is the 4 to 6 year gap. That is the window when, if a Chelyabinsk-class rock arrives from the sunward direction, we will not see it. Not on the 8-day timeline, not on the 8-hour timeline, not at all. The first time anyone on Earth will know it is when it lights up the morning sky as a fireball, and the question becomes, what do we do with that knowledge? One answer is to fund the space-based infrared missions on time. The funding fight that NEO Surveyor went through 3 years ago was not the last. NEO-MIR is still in early study phase, and ESA's space safety budget is not infinite. Both missions are exactly the kind of long-lead, low-glamour infrastructure that gets cut first when budget reviews come around. They are not going to send back pretty pictures. They're going to send back a list of orbital elements and impact probabilities for objects nobody has heard of. The political case for them is harder to make than the case for, say, a Mars sample return, even though the impact case for Mars samples is several orders of magnitude smaller than the impact case for closing the sunward blind spot. Another answer is to keep paying attention to the rocks we do see and learning from them. The 2024 YR4 story is the cleanest example of that we have ever had. Let's take a long look at it next. Because of all the asteroids that have crossed the public consciousness in the last 2 years, YR4 is the one that the system worked on. The one where we watched the probability rise and then watched it fall, and where the journey from one to the other taught us more about how the system actually works than any other asteroid has. But before we get to YR4, let's introduce the concept that makes the whole story make sense. The concept is called a keyhole, and the canonical example of a keyhole is an asteroid that 9 years ago held the title of the most dangerous rock in the catalogue, and is now scheduled to give us, on April 13th, 2029, the closest naked eye flyby of an asteroid in modern history. Its name is Apophis. Part 4. The rocks that almost did not miss. 340 metres across, about twice the height of the Statue of Liberty end to end, 6.1 times 10 to the 10th kilograms, 61 billion kilograms of mass, made of 2 lobes, bilobed shape, like a peanut, like the contact binary asteroid Arakoth that New Horizons flew past in 2019. Mostly silicate rock, with possibly some iron content, spinning slowly on a mostly chaotic axis. Its name in Greek means the Destroyer. In its original Egyptian, it is the name of the serpent god of darkness. Western astronomers picked the name in 2004, when this rock briefly became the most dangerous asteroid we had ever measured. On April 13th, 2029, at 21 hours and 46 minutes. Coordinated Universal Time, asteroid 99942. Apophis will pass Earth at a distance of 31,600 kilometers above the surface, about 19,600 miles. That is closer than geostationary orbit, which sits at 35,786 kilometers. That is inside the ring of communication satellites that broadcast television and route phone calls. From Europe, from Africa, from Western Asia, the asteroid will be visible to the naked eye, reaching magnitude 3.1. that is brighter than the faintest stars in the Big Dipper, a point of light moving across the sky over a span of hours. Hundreds of millions of people in those longitude bands will see it personally. Apophis is not, however, on the current Sentry risk list. Despite the close pass, despite the size, despite the public profile, Apophis is rated Torino 0. NASA and ESA have officially declared that Apophis poses no risk to Earth for at least the next 100 years. The flyby on April 13, 2029 is locked. The flyby on April 13, 2036 is locked. The flyby in 2068 is locked. Apophis will pass close to Earth several times in the coming century, and every one of those passes has been calculated, and none of them is an impact. But here is the thing. As recently as 2021, that was not certain. The 2036 flyby and the 2068 flyby had open possibilities of impact. The mechanism that connected the 2029 flyby to the later possibility of impact has a name. It is called a gravitational keyhole, and understanding the keyhole concept is the key to understanding the entire current asteroid risk catalogue. Here is how a keyhole works. When an asteroid passes close to Earth on one approach, Earth's gravity bends the asteroid's trajectory. The amount of bending depends on the distance of closest approach and on the geometry of the encounter. If the asteroid passes through a specific narrow region of space, a region typically only meters or kilometers wide, then the gravitational bending sends the asteroid onto a future trajectory that intersects Earth on a subsequent flyby. That narrow region of space is the keyhole. Andrea Milani and Giovanni Valsecchi at the University of Pisa formalized the concept in the early 2000s. Paul Chodas at the Jet Propulsion Laboratory developed the operational tools. The B-plane projection, the plane through Earth's center perpendicular to the incoming asteroid's velocity, is where the keyholes are mapped. For Apophis, the 2029 flyby has a 31,600 kilometer closest approach. The uncertainty in the B-plane position is on the order of kilometers. The 2036 impact keyhole was, when first identified, about 600 meters wide. To hit Earth in 2036, Apophis would need to thread that 600-meter gap during its 2029 flyby. To miss the keyhole, Apophis would need to be just slightly off, anywhere outside that 600-meter window. In 2004, when Apophis was first discovered, the orbital uncertainty was much larger than 600 meters. The probability of passing through the keyhole was non-negligible. On December 27, 2004, the impact probability for April 13, 2029 itself peaked at 2.7%. That is Torino 4, only object ever rated that high. The Palermo scale, which is a logarithmic comparison to background impact rate, hit positive 1.10. That means the Apophis threat in late 2004 was about 10 times higher than the background asteroid impact rate, integrated over the time until the encounter. Then, that same day, precovery images of Apophis were found in archives going back to March 2004. The longer arc let the orbit be refined. The Torino rating fell from 4 to 0. The impact probability dropped below background. But the 2036 keyhole remained open. So over the next 16 years, astronomers chased Apophis with increasingly precise observations. Optical photometry, radar pings from the Goldstone Solar System radar and Arecibo. Each observation tightened the orbital uncertainty. Each tightening either confirmed or ruled out keyhole passages. The 2036 keyhole was eventually closed by observations in 2013. The 2068 keyhole, deeper in time and therefore more uncertain, remained open until March 2021. In March of 2021, Goldstone radar made another pass at Apophis as it approached one of its mid-decade close approaches. The radar measurements pinned the position to within a few hundred meters. David Farnocchia at the Jet Propulsion Laboratory and his team published the result. The 2068 keyhole was closed. Apophis was officially removed from the Sentry risk list on February 21, 2021. The asteroid that once held Torino 4, the only object ever to do so, became, by the strict mathematical definition of risk, no longer a risk. That is the keyhole concept in action. A close encounter today can produce a later impact, but only if the asteroid threads a narrow gravitational gap during the close encounter. Every keyhole has a specific position in space and a specific width. Modern astrometry can measure asteroid positions accurately enough to either confirm or rule out keyhole passages. The system works. The April 2029 flyby of Apophis is, in some ways, a planetary defense gift. We get to watch a 340-meter rock pass closer to Earth than the geostationary satellites that broadcast our television. We get to measure exactly how the encounter perturbs its orbit. We get to refine the post-flyby trajectory to high precision and confirm that no 22nd century keyhole opens up. We get to study, in detail, the only large near-Earth asteroid that will pass that close in the foreseeable future. For that purpose, NASA is sending a spacecraft. It is called OSIRIS-APEX. The spacecraft used to be called OSIRIS-REx, which returned a sample of asteroid Bennu to Earth on September 24, 2023. The sample capsule landed at the Utah Test and Training Range, delivering 121.6 grams of regolith, the largest carbonaceous sample ever returned to Earth from any solar system body. After that, the spacecraft itself, with its tanks not fully empty and its instruments still working, was redirected. It was given a new name. APEX stands for Apophis Explorer. It will perform an Earth gravity assist. It has already done one on September the 23rd, 2025, passing 3,438 kilometers above Earth's surface, and arrive at Apophis on April 13th, 2029, in time for the flyby. OSIRIS-APEX will conduct 18 months of proximity operations with Apophis. It will measure the surface in detail. It will watch how the close approach to Earth perturbs Apophis's rotation, its surface, its dust. Hirabayashi and colleagues, in a 2023 paper in Monthly Notices of the Royal Astronomical Society, calculated that Apophis's surface will experience tidal forces strong enough to resurface roughly 1% of the asteroid in the half hour before perigee. Loose surface material will move, boulders may roll, the spin axis may shift. OSIRIS-APEX will measure all of it. At the end of its proximity mission, the spacecraft will descend to fire its engines toward the surface of Apophis and disturb the regolith, just to see what is underneath. OSIRIS-APEX is not the only Apophis mission. The European Space Agency is building a complementary spacecraft called RAMSES, which stands for Rapid Apophis Mission for Space Safety. RAMSES will rendezvous with Apophis before the 2029 flyby, earlier than OSIRIS-APEX, which arrives during or just after, to measure the asteroid's properties before the tidal stress event. That way, the two missions together can characterize Apophis before, during and after the close approach. RAMSES is in development. The funding fight for OSIRIS-APEX was not as visible as the one for NEO Surveyor, but it was real. The fiscal 2026 budget cycle nearly cancelled the mission. The House appropriated $20 million at the last minute to keep it alive. The science community lobbied. The mission survived. $20 million to extend an existing spacecraft fully built, fully tested with a new and unrepeatable mission. A few hundredths of 1% of NASA's annual budget. That is what almost did not get funded. Okay. Apophis is the keyhole concept teacher. It is the rock that illustrates how close approaches connect to future impacts, how the system measures and closes those keyholes, and how spacecraft can study the encounters directly. Apophis itself is not the current threat. The current rocks worth knowing about are different. Let's now talk about the rock that almost was. 2024 YR4. 2024 YR4 was discovered on December 27, 2024, by the Atlas telescope at El Source Observatory in Chile. The Catalina Sky Survey did not see it. Pan-STARRS did not see it. The Hawaii Atlas scopes did not see it. Only the Chilean Atlas scope caught it, 2 days after its closest approach to Earth, which was on December the 25th, 2024, when the asteroid passed about 828,000 kilometers from Earth, or about 2.15 lunar distances. Inbound, the asteroid was approaching from the daytime sky, from the sunward direction, from the half of the sky that the ground-based scopes cannot see. It was not until 2 days after closest approach, when YR4 had moved out of solar glare into the night side, that Atlas Chile detected it. By then, the rock was already moving away. YR4 is about 60 meters across, 3 times the size of Chelyabinsk. The James Webb Space Telescope observed it in March of 2025 during Program 9239, a 5-hour observation that watched the asteroid rotate once every 19.5 minutes. A second JWST observation campaign followed in May 2025. The combined data refined the size estimate to 53 to 67 metres, with composition consistent with stony chondrite, rockier than typical for that size class. Mass, about 220,000 metric tons, with a factor of 10 uncertainty. Predicted atmospheric entry velocity, 17.2 km per second. Hypothetical impact energy, about 7.7 megatons of TNT, within a range from a few hundred kilotons to 15 megatons. The likely outcome of a direct hit, given the stony composition, an airburst over land, not a crater. Now here is where it got interesting. Once YR4 was discovered, the Sentry Impact Monitoring System at NASA and the Meerkat Impact Monitoring System at ESA both took the initial orbit and propagated it forward. They identified December 22, 2032 as the date of the next close approach. The probability of an impact on that date, calculated from the short observation arc, was small but non-zero. On January 27, 2025, the probability crossed 1%. The Torino rating moved from 1 to 3. On February 18, 2025, the probability peaked at 3.1%. The Palermo scale hit -0.18. Torino 3, held there for 24 days. To put that in context, only Apophis had ever rated higher on the Torino scale, and only for a few hours of December 27, 2004. YR4 held Torino 3 for 24 days, the second highest Torino rating in history, the first asteroid in 20 years to make the news for that reason. Mainstream coverage predictably called it a city killer. CNN, Scientific American, Live Science, NPR, all of them used that phrase. A 60-metre rock airbursting over a city would indeed kill a city. The framing was not wrong. The probability was small but not zero, and the probability was rising as the short observation arc dominated the orbital solution. Then the arc lengthened. Astronomers around the world chased YR4. The Bock telescope at Kitt Peak observed it. The Magellan telescopes in Chile observed it. The European Southern Observatory's VLT observed it. The Gemini South Telescope observed it. Sam Dean, an amateur orbital archaeologist, found a recovery image in the Intermediate Palomar Transient Factory archives, going back to 2016, extending the arc to 9 years. By February 23, 2025, the observation arc had reached 60 days and the Torino rating dropped to 0. By April 2, 2025, the arc had reached 91 days, and NASA officially eliminated the Earth impact possibility entirely. David van Nokia at the CNEOS office, speaking at the Small Bodies Assessment Group meeting in June 2025, called it textbook expected behaviour. The probability rose as the short observation arc dominated. The probability fell as the arc lengthened. The system did not fail. The system did exactly what it was designed to do. It told us transparently that an object had a non-zero impact probability, and then it told us transparently that the probability had been driven to 0. But the Earth impact branch of the YR4 story is only half of it. The other half was the Moon. After Earth was ruled out, ESA and NASA both noticed something else. There was a residual probability that YR4 would hit the Moon on the same date, December 22, 2032. The probability was about 3.8% in April 2025, the same time Earth was eliminated. Over the following months, the lunar probability rose to about 4.3%. That meant a 1 in 23 chance that humanity's lifetime would include the first known asteroid impact on the Moon, visible in real time from Earth, a 60-metre rock excavating a crater on the lunar surface, recorded by every telescope and spacecraft pointed at the Moon. For most of 2025 and into early 2026, the lunar branch held. Astronomers speculated about the implications. A direct impact on the Moon would not threaten Earth, but it would throw debris into space, some of which could intersect satellites in Earth orbit. It would create a new crater visible in lunar imaging. It would let us watch, for the first time in history, an asteroid impact on a planetary body at high resolution, in real time. Then came February 2026. 2 more JWST observations of YR4. The orbital uncertainty tightened again. The lunar impact probability dropped from 4.3% to 0. On March 5, 2026, NASA's Planetary Defense blog announced, YR4 will pass the Moon on December 22, 2032, at a distance of 21,200 kilometers, about 13,200 miles. No impact, just a flyby. The YR4 story is, in its entirety, the cleanest demonstration we have of the planetary defense system working as designed. An object was discovered late, because it approached from the day side and was only seen after it passed. The probability of impact rose with short arc. The probability fell with longer arc. JWST was called in for refined astrometry. The Earth branch closed. The lunar branch persisted, then closed. Throughout, the system was public, transparent, and predictable. The lesson for the documentary thread of this video is that the system does work for the rocks it can see. The probability rise from 1 to 3 on the Torino scale was not a failure. It was the system doing math out loud, in public, with full transparency. The journalists who covered it as alarm were not wrong to do so. Torino 3 is genuinely alarming statistically, but the eventual resolution was the only resolution the math allowed. The harder question, the one this video is trying to land, is what happens when the system cannot see the rock at all. YR4 was caught 2 days after its closest approach. The same geometry would mean, for a future arrival, that the rock would not be detected until after it had hit. That is what Chelyabinsk did. That is what the Ohio bolide of March 17th did. That is what the rocks in the sunward blind zone will do. Now let me close this part by mentioning the current Sentry risk list. As of late December 2025, the list has 2 objects with cumulative Palermo scale above -2. The first is Asteroid 1950DA, about 1.3 kilometers across. Cumulative impact probability of about 1 in 51,000. Palermo -0.93. Possible impact date, March 16th, 2880, about 854 years from now. The second is Asteroid 101955 Bennu, which is the asteroid that OSIRIS-REx sampled and returned to Earth, about 490 meters across. Cumulative impact probability through year 2300, 1 in 1750. Palermo -1.40. Peak probability date, September 24th, 2182, about 156 years from now. Below those two, the Palermo numbers drop quickly. 2008 JL3 at -2.68. 1979 XB at -2.69. 2000 SG 344 at -2.77. 2010 RF12 at -2.97. All of them well below background impact rate. None of them rated above Torino 0, none of them current Earth threats. The Sentry list in May 2026 is unusually quiet by historical standards. After YR4 was resolved, the list returned to a baseline that has held for years. The catalogue at 1 kilometre is essentially complete. The catalogue at 140 metres is 40% complete. The catalogue at 20 metres, the Chelyabinsk class, is essentially non-existent. And the sub-20 metre rocks are caught only when they come close enough to be seen, on the order of days, by the surveys that can see the night sky. That brings us to the 11 rocks that humans actually predicted before they hit Earth. And the 12th, 3 days ago. Let's look at every one of them. Let me give you a sense of just how dark the night side of Earth's sky actually is from a clean observatory site, and just how bright the day side is, because the numbers themselves are worth pausing on. At a dark observatory location at zenith, away from the Milky Way and the Moon, the sky brightness in the V-band corresponds to a magnitude of about 21.7 per square arc second. That is dim. By contrast, the daytime sky at noon at the same observatory, with the sun 90 degrees away, has a sky brightness of roughly magnitude -4.5 per square arc second. The difference is about 26 magnitudes per square arc second. Each 5 magnitudes is a factor of 100. 26 magnitudes is a factor of nearly 40 billion. The daytime sky is 40 billion times brighter than the night sky in optical wavelengths. Square arc second for square arc second. Pretend you're looking for a faint moving point of light. The detection threshold of even the deepest current ground-based asteroid survey is somewhere around apparent magnitude 22. That is what Catalina and Atlas can pull out of the noise in a 30-second exposure under dark sky conditions. To detect a point source at magnitude 22 against the daytime sky, you would need a sky background that was 40 billion times darker than the daytime sky actually is. You cannot get there from the ground in optical wavelengths, not with bigger telescopes, not with longer exposures, not with better software. The photon arithmetic does not allow it. the faintest point you can detect against a daytime sky is something like magnitude -3 or -4, which is to say, the brightest visible planets at their brightest. Asteroids even close to Earth are nowhere near that bright. That is what the blind spot really is. 40 billion to 1 in optical wavelengths, closed by physics. The thermal infrared is different. The sky at 6 to 10 microns, even in the daytime, is bright but not unmanageably so, because the bulk of the sun's radiation in those wavelengths is much smaller than in optical bands. Most of the daytime sky brightness in the infrared comes from thermal emission of the atmosphere itself, which is why ground-based infrared astronomy is hard regardless of solar elongation, and why infrared astronomy works much better from space. From L1, above the atmosphere, looking outward, an infrared telescope can detect a thermally emitting asteroid against a sky background that is roughly as dark in the day side as in the night side. That is why NEO Surveyor and NEO MIR are infrared. Not for sentimental reasons, because the photon arithmetic at 6 to 10 microns finally cooperates. Let me also pause to acknowledge something about the small NEO catalogue. The current best estimate of the total number of near-Earth asteroids 1 meter or larger is somewhere between 10 million and a few hundred million. Of those, we have catalogued about 37,000. That is, depending on which population model you trust, somewhere between 0.1 and 1% of the small-end NEO population. Most of the rest are sub-meter, and the rate at which they hit Earth is not low. By some estimates, several meter-class or smaller rocks enter our atmosphere every week, most of them over open ocean or polar regions or remote land where nobody sees them. The CNEOS Fireball database is, in some sense, a catalogue of the meter-scale entries that happen to be witnessed by infrasound arrays or by US government sensors. The actual rate of small atmospheric entries is far higher than the witnessed rate. Most of them, even the ones over populated areas, are too small to do damage. They burn up at 30 to 50 kilometers altitude, and the only sign is a brief flash. What this means for the public-facing question of asteroid risk is something like the following. The major impactor risk, kilometer-class civilization changing, is essentially solved. We have catalogued more than 90% of the kilometer-class population. None of them have a non-negligible impact probability this century. The 140-meter class, regional disasters, is half solved. The catalogue is 40% complete. NEO Surveyor will push that toward 90%. The sub-140-meter class, the Chelyabinsk to City Block range, is essentially not solved. The catalogue is well below 1% complete, and the geometry that allows objects to hide in solar glare specifically biases the unknown population toward Atira and Vatira orbits. These are the rocks that arrive without warning sometimes, and have done so before. The expected outcomes are not symmetric. A direct hit by a Chelyabinsk-class object in a populated area would, based on the actual Chelyabinsk event, injure tens of thousands of people with flying glass and damage tens of thousands of buildings. It would not destroy a city. It would not kill thousands. It would, however, be the largest natural disaster news event of its day, and the largest impact event of the modern era. If the next one airbursts over a denser urban core than Chelyabinsk, over Manhattan, over Tokyo, over Mumbai, the damage scales non-linearly with population density. Glass damage in dense vertical cities is far worse than glass damage in semi-rural, Russian provincial cities. The injury count could be much higher. That is the asymmetric risk profile that justifies the cost of the space-based infrared missions. A one-time investment of $1 billion or $2 billion now to catalogue and characterise Atira and Vatira class asteroids against a tail risk of 100,000-person glass injury events somewhere in the next century. The math on any reasonable estimate supports the investment. The fight to fund the missions has not been about the math. It has been about institutional priorities and budget cycles. The math, when it is allowed to speak, has been clear. There is one more thing about the YR4 story worth knowing, because it is the part that almost did not happen. In late January 2025, when the impact probability for the December 2032 encounter crossed 1%, the planetary defense community had a problem. The asteroid was at about magnitude 25 at the time of the rising probability calculation. Magnitude 25 is well below what most observatories can reach in routine operations. The orbital arc was short. To get the longer arc that would either confirm the threat or refine it away, astronomers needed to keep observing the asteroid as it faded. The Magellan twin telescopes at Las Campanas in Chile, the Very Large Telescope at the European Southern Observatory in Chile, and the Gemini South Telescope, also at Cerro Tololo, all gave time to chase YR4. Telescopes that normally observe galaxy clusters and exoplanet-host stars and quasar absorption features were pointed at a single, faint, fast-moving point of light night after night for weeks. The reason is that no smaller telescope could reach it. Then, in March 2025, the James Webb Space Telescope took its first look. JWST is not optimized for asteroid astrometry. It is a multi-billion-dollar infrared observatory whose primary mission is the early universe, exoplanet atmospheres, and galaxy formation. Director's discretionary time was granted for YR4 because the planetary defense case rose to the level of warranting it. The observation was Program 9239, 5 hours of telescope time. The output was a thermal infrared light curve and a precise position measurement that immediately drove the orbital uncertainty down by an order of magnitude. The Earth impact probability dropped within days of the JWST data being processed. The system that took 24 days at Torino 3 folded its conclusion the moment the Better Instruments data arrived. Then, in May 2025, a second JWST observation. Then, in February 2026, 2 more. Each one tightened the orbital uncertainty further. The Earth branch closed, then the Moon branch closed. The point of recounting this in detail is not to celebrate JWST. It is to note that the entire chain of saving, of taking a Torino 3 rock that was rising toward a possibly imminent catastrophe and walking it back through the math to zero, required the most expensive single scientific instrument ever built to do its other job for a few hours. If JWST had not been operating in 2025, the orbital refinement would have come slower, the Torino rating would have stayed elevated longer, and the public pressure response might have driven a more frantic political reaction. The system worked because the resources were available. In the case of a sunward blind spot rock that arrives without warning, none of the JWST refinement matters. There is no rock to observe, there is no orbit to refine. There is no Torino number that ever lights up because nothing was ever detected in the first place. The system that worked beautifully on YR4, surveys, Sentry, JWST, ESA Meerkat, the whole orchestrated response, operates only on objects that have already been put into the system by a successful detection. For the rocks that never enter the system, the response is mute. That is the operational difference between the visible kind and the invisible kind asteroid threat. The visible kind is what we have built infrastructure for. The invisible kind has, as of May 2026, no infrastructure pointed at it. NEO Surveyor will be the first. Let me also say something about how the warning chain actually reaches people, because this is the part of the system that the public rarely sees and that, frankly, has not yet been stress tested for a real Chelyabinsk-class object. The International Asteroid Warning Network operates a notification protocol. When an impact probability for an object greater than 10 meters crosses 1%, the network triggers. The first call goes from the Impact Monitoring System, Scout at CNEOS, or Meerkat at ESA, to the Planetary Defense Officers at NASA and ESA. The Planetary Defense Officers verify the calculation. The UN Office for Outer Space Affairs is informed. Then the IAWN Steering Committee is convened. The steering committee includes representatives from observatories, space agencies, civil protection authorities, and the UN. The committee assesses the threat and, if warranted, issues a notification to member states. Member states are then responsible for relaying the warning to their own civil defense systems. In the United States, this would be the Federal Emergency Management Agency and the Department of Homeland Security. In Europe, the European Union's Civil Protection Mechanism. In Japan, the National Disaster Management Agency, and so on. The chain has been exercised in tabletop simulations. The Space Mission Planning Advisory Group, SMPAG, holds annual tabletop exercises in conjunction with the IAA Planetary Defense Conference. The most recent conference, the 9th Planetary Defense Conference, was held in Cape Town, South Africa in May 2025. The scenario for the tabletop was a hypothetical asteroid designated 2024 PDC-25, which by the Epoch 2 update was projected to impact Earth on April 24, 2041, with 100% certainty. The scenario gave 13 years of warning. The SPAG group held weekly teleconferences from the August scenario start through the conference, and an in-person meeting in Milan in October 2024. The outputs included recommended deflection mission architectures, both kinetic impactor and nuclear options, and evacuation strategies for the projected impact zone. The tabletop exercise was the first PDC scenario to integrate higher education public engagement. The recommendations went to a decision-makers panel. What the tabletop did not exercise, because no tabletop ever has, is a real-world scenario where the warning is 2 hours instead of 13 years. That has not happened. The 12 real predicted impactors so far have all been small enough that the IAWN formal threshold was not technically tripped. The system has been used informally, with the planetary defense offices sending direct notifications to relevant national authorities, but the full chain has never been activated for an actual threat. If a Chelyabinsk-class object were detected at, say, 3 days out, with a high impact probability and a confidence on the impact location, the full chain would activate for the first time. How well it would work is not certain. The chain has not been tested at speed. What is certain is that until NEO Surveyor begins operations in late 2027 or 2028, and NEOM-IR follows a few years after that, a Chelyabinsk-class object from the sunward direction would not be detected in time for the chain to activate at all. Zero warning, just like 2013. That is the system. That is the gap. That is what the news did not tell you about Monday's flyby. One more thing about Apophis, because it deserves it. The story of how Apophis went from Trino 4, the most dangerous asteroid ever measured, to officially eliminated is in some ways the most reassuring story in the planetary defense canon. On December 27, 2004, the impact probability for April 13, 2029 was 2.7%. By the end of the same day, after Precovery images extended the arc, it was below background. The whole Trino 4 event lasted about 8 hours. The deeper story, the 2036 keyhole closure in 2013, the 2068 keyhole closure in 2021, took years of patient observation. Goldstone radar passes during the asteroid's intermediate close approaches. Optical photometry at successive perihelions. Each pass tightened the orbit a little more. Each tightening either kept the keyhole open or closed it. By March 2021, the 2068 keyhole was closed, and Apophis was, by the strict mathematical definition of the Sentry Risk List, eliminated. The Apophis story is the proof of concept that the system works in the long run for the rocks we can see. The orbits can be refined, the probabilities can be driven to zero, the keyholes can be closed. Apophis went from the most dangerous rock ever to the safest rock ever in 17 years. That is what patient observation does. Osiris-Apex, by the way, is now in cruise mode following its September 2025 Earth gravity assist. The spacecraft is on a trajectory that will bring it to Apophis on April 13, 2029, roughly coincident with the closest approach to Earth. Apex will then drop into a proximity orbit and conduct 18 months of detailed observations. At the end of the mission, Apex will descend toward the surface and fire its engines to disturb the regolith for the first direct measurement of the subsurface mechanical properties of an irregular near-Earth asteroid. That is the only mission we currently have in flight that will directly study what a tidal stress event does to a small body. Ramses, the ESA companion mission, is still in development. Its planned arrival is before the 2029 flyby, which would let us measure Apophis before, during and after the tidal stress event. The funding case for Ramses has, like every space safety mission, been a fight. ESA has supported it. Whether it flies on schedule depends on the next 2 budget cycles. Both missions are essentially first of their kind. We have never had a chance to study a 340-meter asteroid this closely, this safely, with this much warning. The April 2029 flyby is a generational planetary science opportunity. For the public, it is the closest naked-eye asteroid in modern history. For scientists, it is the only direct measurement of tidal physics on a non-Earth impacting body we will get for a long time. It is also a reminder of what the system can do when it has decades to work. For an object the size and orbit of Apophis, decades is what was needed. For an object the size and approach geometry of Chelyabinsk, hours would be needed. The system is not yet built for the second case. I want to close out the predicted impactor stories with one detail about 2024 BX1, the Berlin Rock, because it is the cleanest demonstration of what the system can do when everything works right. Sarnecki discovered the object at 21:48 Coordinated Universal Time. The Scout system at CNEOS generated an automated impact prediction at 22:58, 70 minutes later. The predicted impact location was an ellipse centered about 60 kilometers west of Berlin, with a long axis of less than 100 kilometers. The predicted impact time was 0033, Coordinated Universal Time on January 21st, 2 hours and 45 minutes after discovery. That window, 2 hours and 45 minutes, is what stands between detection and entry for a 1 meter rock. There is no policy choice involved. Detection works for 1 meter, deflection does not, evacuation barely. Notification to the immediate population, broadcast warning to stay indoors and away from windows, is the only operational response that fits inside the time budget. The German authorities were notified. The fireball arrived at exactly the predicted time. Stones were on the ground in fields around Ribbeck the same morning. The orbite recovery was complete within days. The system worked perfectly. The rock was small enough not to matter. The Scout prediction was accurate to within 1 second and 100 meters. The civil protection notification reached people. Nobody was hurt. Meteorites were recovered. Science was advanced. This is the success case. The success case requires the rock to be detected. It requires the rock to be observable. The rock has to be on the night side, at sufficient solar elongation, large enough to be visible at the distance at which it is found, fast enough to give a few hours of orbital determination. For all the rocks in the predicted impactor catalogue, those conditions held. For the rocks they did not hold for Chelyabinsk, the Ohio bolide of March 17th this year, and the unknown number of meter-class objects that have hit polar regions, deep ocean, and uninhabited deserts without anyone seeing them. There is no success case. There is only the after-action CNEOS fireball entry, recorded by infrasound or by satellite optical detection. The 11 cases, 12, with the Arafura Sea event 3 days ago, represent every time the system worked. They are not a complete record of every asteroid impact since 2008. They are a complete record of every asteroid impact since 2008 that we predicted in advance. The two are different. The difference is the blind spot. Now back to the operational reality of Monday's flyby of JH2. The Virtual Telescope project's live stream begins at 1945 Coordinated Universal Time on May 18th. That is 1 hour, 38 minutes before geocentric closest approach. Gianluca Massi will operate his telescope at Ceccano, in central Italy, from his usual control centre. The asteroid will be at apparent magnitude approximately 11.5 during the live stream, well within reach of his 14-inch instrument. Viewers around the world will see the bright moving point of light against the star field as JH2 crosses the celestial equator from north to south. The closest approach itself, at 91,300 kilometers above Earth's surface, though to be precise it is the geocentric centre-to-centre distance, will not be visible from Earth as a notable event. The asteroid will not flash. It will not visibly speed up. It will simply trace its arc across the sky over the course of hours, moving from constellation to constellation as Earth's rotation carries observers and the rock continues its parabolic path. From most amateur telescopes, the visible track will be a slow drift that resolves into motion over 30 seconds or a minute. Photographs will show the streak. Time-lapse imagery will show the speed. It is a small event by any astronomical standard. A 20-meter rock passing inside the Moon's orbit, observed by amateur telescopes, live-streamed by an Italian operator, watched by a few 100,000 interested viewers around the world. The most dramatic moment of the encounter, ironically, will be the moment when the world's news organizations stop covering it, because no impact occurred and the headlines moved on. But the question the encounter raises, the question the news framed wrong and that this video has tried to frame right, does not go away when the asteroid does. The half of the sky we cannot see remains exactly where it has always been. The rocks that come from it remain exactly as undetected as they have always been. The next Chelyabinsk-class object, whenever it arrives, will arrive from somewhere. We do not know from where. The probability that it arrives from the sunward direction, given that roughly half the geometry of near-Earth asteroid orbits favours sunward approach, is somewhere around 50%. Not for the next year, not for the next decade, but across the timescale of expected Chelyabinsk-class events, once every 50 to 100 years, on average. 50% of those events will come from a geometry we cannot currently watch. That is the long-run probability that justifies NEO Surveyor's billion-dollar price tag. That is the long-run probability that justifies NEOMIR. That is the long-run probability that the congressional intervention in the CHIPS and Science Act was protecting against. And it is the probability that explains why Monday's JH2 flyby is not, in any meaningful sense, the asteroid story of this week, this month, or this year. The flyby is real. The asteroid is real. The 8 days of warning are real. But the rock that will land somewhere, sometime in this century or the next, the one we do not yet know about, the one that is right now an undiscovered orbital trace in the catalogue we have not built, is the story that matters. It is the story the news did not tell. It is the story I have just told you. Part 5. The 12 times we were right. On the morning of October 6th, 2008, at 6:39 Coordinated Universal Time, a young observer named Richard Kowalski sat at the controls of the Mount Lemmon Survey Telescope outside Tucson, Arizona. The telescope had just finished a scan of a patch of sky west of the constellation Orion. The software flagged a faint moving object at apparent magnitude 20.5. Kowalski submitted the astrometry to the Minor Planet Center. A few hours later, a designation came back, 2008 TC3. What happened next had never happened before in human history. The orbit solver at the Minor Planet Center and then the impact monitoring system at the Jet Propulsion Laboratory looked at the short observation arc and concluded that 2008 TC3 was not going to miss Earth. It was going to hit. The predicted impact time was approximately 20 hours after Kowalski's discovery. The predicted impact location was somewhere over northern Sudan. Telephones rang. The Catalina Sky Survey notified NASA. NASA notified the Department of Homeland Security. The Department of Homeland Security notified relevant international partners. The European Space Agency activated its preliminary impact monitoring response. The Steward Observatory at Kitt Peak began follow-up astrometry. The Tautenberg-Schmidt telescope in Germany observed it. By the time the rock entered the atmosphere, the observation arc had grown from 70 minutes to nearly 24 hours, and the orbital solution had narrowed the impact location and time to within minutes and kilometers. At 2:46 Coordinated Universal Time on October 7th, 2008 TC3 entered Earth's atmosphere at 12.8 kilometers per second over the Nubian Desert, latitude 20.8 degrees north, longitude 32.2 degrees east. The asteroid was 4 meters across, about 80 metric tons in mass. The airburst occurred at roughly 37 kilometers altitude. The energy released was somewhere between 0.9 and 2.1 kilotons. A meteorological satellite caught the explosion as a bright flash in infrared imagery. An airline pilot flying nearby reported a brief flash. 2 months later, in December 2008, an expedition led by Peter Jenniskens of the SETI Institute and Muawiyah Shahdad of the University of Khartoum walked the Wadi Halfa to Khartoum railroad line, looking for fragments. They found 15 meteorites in the first 3 days. By the time the search was complete, hundreds of stones had been recovered, totaling about 10 kilograms. They named the meteorite Al-Mahata Sitta, which is Arabic for Station 6, after the railroad station closest to the strewn field. 2008 TC3 is the first object in human history that we detected in space, predicted to impact Earth, watched impact, and then recovered samples from. The recovery rate is about 1 fragment per 180 cubic kilometers of desert. The recovery of Al-Mahata Sitta meteorites confirmed something extraordinary. The asteroid composition matched a class called Uralites, an unusual carbon-bearing achondrite that scientists had been studying for decades from older meteorite falls of unknown parentage. 2008 TC3 gave us for the first time a direct match between an asteroid observed in space and a meteorite type known on Earth. The total warning time from Kowalski's discovery to atmospheric entry was 20 hours and 7 minutes. That was 2008. Then came a long gap. Then it happened again. On January 1st, 2014, again from Mount Lemmon, again Richard Kowalski. Asteroid 2014 AA. Discovered at 6:18 Coordinated Universal Time on New Year's Day. The observation arc was only 70 minutes before atmospheric entry was predicted, at approximately 3:06 Coordinated Universal Time on January 2nd. The predicted impact location was the Atlantic Ocean, about 1,900 kilometers east of Trinidad. The rock was estimated at 2 to 4 meters across. There were no immediate witnesses. The ocean is a poor recovery field. But 3 infrasound stations operated by the Comprehensive Nuclear Test Ban Treaty Organization recorded the airburst, which let post-event analysis refine the impact location and time. The official confirmation came hours later. 2014 AA was the second predicted impactor. Warning time 21 hours, then another long gap, 4 years. Then, on June 2nd, 2018, at 8:14 Coordinated Universal Time, the Mount Lemmon survey caught its third predicted impactor, 2018 LA. The orbital solution gave a predicted impact about 8 hours later, with the impact zone in southern Africa. The first calculation predicted somewhere between Australia and Madagascar, with about 85% probability for a strip across the Botswana and South Africa border. As more astrometry came in, the prediction narrowed. By the time the rock entered the atmosphere at 1644 Coordinated Universal Time the same day, the impact point was nailed down to the Central Kalahari Game Reserve. 2018 LA was 3 meters across, give or take a half meter. The fireball was witnessed and filmed from multiple ground locations. Peter Jenniskens led another recovery expedition. The first meteorite was found on June 23, 2018, by a team led by Jenniskens and the Botswana Geoscience Institute. They named the meteorite Matopi Pan, after a nearby waterhole. Lab analysis showed something remarkable. Matopi Pan's isotopic signature was consistent with the asteroid Vesta. That meant 2018 LA was a fragment of Vesta, blasted off the third largest body in the asteroid belt sometime in the past, drifting on its own elliptical orbit until it caught Earth 8 hours after we found it. Warning time 8 hours, a year later. 2019 MO, discovered on June 22, 2019, by the Asteroid Terrestrial Impact Last Alert System Telescope on Mauna Loa, Hawaii. Atlas-MLO. Warning time 12 hours. Impact in the Caribbean Sea south of Puerto Rico, 3 to 6 meters across. No meteorite recovery. Ocean. This was the first Atlas-discovered imminent impactor. Then there is a pause that you should notice. Between 2008 and 2019, we predicted 4 impacts, roughly 1 every 3 years, then the pace picks up. On March 11, 2022, at 1924 Coordinated Universal Time, a Hungarian astronomer named Krisztián Sarnecki at Piszkesteto Station in the Matra Mountains of northern Hungary caught a faint object on his 60-centimeter Schmidt telescope. He submitted the astrometry. NASA's Scout system flagged it as an impactor within minutes. The predicted impact was just under 2 hours later, at 21:22 Coordinated Universal Time the same evening. Impact location: the Norwegian Sea, about 140 kilometers southwest of the volcanic island of Jan Mayen. The rock was about 2 meters across. The infrasound arrays at Spitsbergen and Greenland recorded the airburst. Yield about 4 kilotons. Warning time 2 hours, the 5th ever and the shortest to date. Sarnecki was not done. On February 12, 2023, at 2018 Coordinated Universal Time, he caught another one. Provisional designation SAR 2667, later 2023 CX1. Predicted impact about 6.5 hours later over the English Channel coast of Normandy, France. The rock was about 1 meter across. The impact happened at 2:59 Coordinated Universal Time on February 13th. The fireball was widely seen across northern France. 3 days later, on February 15th, 2023, at 15:47 Coordinated Universal Time, a volunteer for the French fireball network Fripon, named Lois Leblanc, walked a field in the commune of Saint-Pierre-le-Viger in the Seine-Maritime department and picked up the first meteorite. Over the next several months, more than 20 stones were recovered, ranging from 2 grams to 350 grams. The classification, L5 to L6 ordinary chondrite. Boring scientifically, historic operationally. 2023 CX1 was the 7th predicted impactor, the second with recovered meteorites in Europe, and Sarnecki's second discovery. Then, before 2023 CX1 had even been fully analysed, another one, 2022 WJ1, November the 19th, 2022. Discovered by David Rankin of the Catalina Sky Survey, on the Met Lemon 1.5 meter telescope, 3.5 hours of warning. Impact zone, the south shore of Lake Ontario between Grimsby and Niagara-on-the-Lake. The rock was sub-meter, the smallest known asteroid in space ever recorded, about 40 centimeters across. Most fragments fell into Lake Ontario. One small piece was recovered near the Grimsby community. 6th predicted impactor, then Sarnecki again. January 20th, 2024, at 21:48 Coordinated Universal Time. Provisional designation SAR 2736. Later, 2024, BX1. The Scout system locked a 100% impact prediction within 70 minutes of discovery. Predicted impact location, about 60 kilometers west of Berlin, near the village of Ribbeck in Brandenburg. Predicted impact time, about 3 hours after discovery, just past midnight Central European Time on January 21st. The actual impact happened at 00:33 Coordinated Universal Time, exactly as predicted. The fireball was seen across Germany, Poland and the Netherlands. Recovery began the same day. Teams from the SETI Institute and the Museum for Naturkunde in Berlin walked the predicted strewn field around Ribbeck. They found stones. Lab analysis showed the meteorite was an obrite, an extremely rare achondrite that has been linked to a parent body somewhere in the inner solar system, possibly related to the asteroid Hungaria. The Ribbeck obrites are now among the most studied meteorites of their class. And in a delightful side note, 2024 BX1 was determined to be the fastest rotating natural object ever measured. 2 hours, 45 minutes of warning. A few months later, in September 2024, the Catalina Sky Survey's Jacqueline Fazekas caught the 9th, 2024 RW1. Discovered 6:39 Coordinated Universal Time on September 4th. Predicted impact, 10 hours later, off the coast of northeastern Luzon, Philippines. The rock was about 1 to 2 meters across. Atmospheric entry velocity, 20.6 kilometers per second, the fastest impact ever predicted. The fireball was filmed from multiple locations on Luzon, despite Typhoon Yagi cloud cover. The prediction was accurate to within 100 meters and 1/10 of a second. Then, on October 22nd, 2024, Atlas Hawaii caught a 10th object. Provisional name A11DC6D, officially designated 2024 UQ. The rock was about a meter across. It impacted at 10:54 Coordinated Universal Time, west of Los Angeles in the Eastern Pacific. The catch with this one was that the moving object recognition software had a slight delay because the rock crossed 2 adjacent CCD fields, so the astrometric data did not reach the impact monitoring systems until after the impact had already occurred. Effective warning time, 0. But the pre-impact images existed in the survey stream, and the prediction was retrospectively confirmed. The 10th predicted impactor, technically. Then, on December 3rd, 2024, the Bok 2.3 meter telescope at Kitt Peak National Observatory, operated by the Spacewatch program, caught the 11th, 2024 XA1. Predicted impact, about 10 hours later, over the Sakha Republic, Yakutia, in northeastern Siberia, near the town of Olekminsk. The rock was less than a meter across. The fireball was widely observed in the pre-dawn Siberian twilight. No confirmed meteorite recovery as of yet, and then, 3 days ago, the 12th. May 15th, 2026, at 13:44, Coordinated Universal Time, Asteroid 2026 JN4 entered Earth's atmosphere over the Arafura Sea, between Australia and Papua New Guinea. The rock was less than 1.5 meters across, somewhere between 0.6 and 1.4 meters, by current best estimate. H magnitude 33.1. The European Space Agency's Meerkat system and NASA's Scout system both flagged a high impact probability from the short observation arc. The warning time on 2026 JN4 has not been publicly specified in detail, but it was on the order of hours. The atmospheric entry was confirmed by infrasound and probably by satellite optical detection 3 days ago, 3 days before JH2 will fly by Earth, the 12th. Now look at that sequence. The first 4 predictions were spread across 11 years. The next 8 have happened in 4 years. The pace is accelerating. The reason is not that more rocks are arriving. The reason is that the surveys are improving. Atlas expanded from 2 telescopes to 4. Catalina added the Bock and the Schmidt programs. Twilight observations are running every clear night at multiple observatories. The Scout and Meerkat impact monitoring systems can lock a prediction within minutes of the first astrometric data hitting the minor planet center. But look at the warning times. They are getting shorter, not longer. 2008 TC3 got us 20 hours. The next 4 got 8 to 21 hours. The most recent 6 all got under 12 hours. 3 of the most recent 6 got under 4 hours. 2022 EB5 gave us 2 hours. 2024 BEX1 gave us less than 3. 2024 UQ gave us 0. The warning times are getting shorter because the rocks are getting smaller. A meter-class object becomes visible to current surveys only when it is within about 100,000 kilometers of Earth. At that distance, even moving at 20 kilometers per second, you only have a few hours before atmospheric entry. The detection physics simply does not allow for more warning on objects of that size. Improvement in survey capability, bigger telescopes, more telescopes, faster image processing, better software, will not change that. The fundamental scaling relationships of reflected sunlight versus distance versus radius are physics, not engineering. What is improving is the precision of the prediction once the rock is detected. 2014 AA had a 5-minute and several hundred kilometer impact prediction window. 2024 RW1 had a 1/10 of a second and 100-meter window. The astrometry is more accurate. The orbital propagation is more accurate. The atmospheric entry modelling is more accurate. Once we see the rock, we can tell people exactly where and when it will arrive. The improvement is real. It is just an improvement in precision, not in lead time. This matters for what we can actually do. If we have 2 hours of warning and the rock is going to land in the Norwegian Sea, the response is to issue a NOTAM to aviation and a maritime advisory and let people watch the fireball. If we have 10 hours and the rock is going to airburst over open ocean, same response. If we have 8 hours and the rock is going to airburst over the central Kalahari, you can evacuate any nearby villages and recover meteorites afterward. If we have 3 hours and the rock is going to airburst over the suburbs of Berlin, you can warn people to stay indoors and away from windows. The system functions for objects that small. None of them have hurt anyone. But the system functions only for the rocks we see. The rocks we do not see do not show up in this list. There are no entries for 2013 Chelyabinsk. There are no entries for March 17th, 2026 Ohio. There are no entries for the dozens of small bolides that hit somewhere on Earth every year that we never see, including the ones over remote oceans, polar regions, and uninhabited deserts. The CNEOS Fireball database catalogues them after the fact, from infrasound and from satellite-based optical detection. But pre-impact warning for any of them was 0. That is what closes the 11-event success record. The record only includes the visible kind. The invisible kind, the kind from the sunward direction, the kind from Atira orbits, the kind from inside Atira orbits. Those rocks do not appear in this catalogue at all. We have not predicted them. We will not predict them, not until the space-based infrared missions fly. Christian Sanecki is a Hungarian high school geography teacher who became an amateur astronomer in his 20s, joined the Konkoly Observatory as a visiting astronomer in 1997, and has now discovered 3 of the 12 predicted impactors: 2022 EB5, 2023 CX1, 2024 BX1. More than any other single observer, he uses a 60cm Schmidt telescope at Piszkesteto Station in the Matra Mountains. Hungarian time zone gives him European nights at a longitude not covered by the US and Hawaii surveys. His method is systematic. He scans the Minor Planet Center's near-Earth object confirmation page for unconfirmed candidates, then immediately follows up. He uploads astrometry the moment he has it. The Scout system at CNEOS checks every new submission. If the orbital solution shows an impact, the alarm goes out. The infrastructure behind all of this is the International Asteroid Warning Network. The UN General Assembly endorsed it through the Committee on the Peaceful Uses of Outer Space in 2013. It was officially established in 2014. Its operational threshold is an impact probability greater than 1% for objects larger than 10 meters across, H magnitude 28 or brighter. The custody chain goes from survey to Minor Planet Center to automated impact monitoring at NASA, CNEOS and ESA-NEO, Coordination Center to the Planetary Defense Offices at both agencies, to the IAWN Steering Committee, to the UN Office for Outer Space Affairs to UN member, states and national civil protection authorities. For sub-10 metre objects like nearly all 12 of the predicted impactors above, the formal threshold is not technically tripped, but the Planetary Defence Offices send informational notifications. ESA's Meerkat service, operational since 2021, has caught every imminent impactor since launch. NASA's Scout system has been catching them since before that. The system works. For the rocks it can see. Now let's step back. Part 6. The document inside the room. There is a thing that happens when you cover stories like this on YouTube. People show up in the comments with theories. Some are interesting, some are not. Most fall into a few recognizable patterns. I want to handle the patterns directly, because if I do not, the comments will, and the comments are not the place for an honest discussion. The first pattern is the framing that the government is hiding incoming impactors, that, if a rock were on a collision course with Earth, NASA and ESA would suppress the information until it was too late to prevent panic. This framing is falsifiable. The Minor Planet Center is a public clearinghouse. Astrometric observations from Atlas, from Catalina, from Pan-STARRS, from Piscesteto, from Box Spacewatch, and from dozens of amateur observatories around the world are uploaded automatically and indexed publicly. The Sentry Risk List at CNEOS is updated in real time. The European Space Agency runs a parallel and equally public risk list at the NEO Coordination Centre. Concealing a predicted impactor would require simultaneously compromising every one of these independent systems and concealing the work of every amateur observer, including the Hungarian high school teacher who has discovered 3 of the 12 predicted impactors so far. The track record alone, 12 predictions, all public, all with full astrometric data and orbital solutions, falsifies the concealment hypothesis. The second pattern is the framing that predicted impacts could be prevented if the authorities wanted to, that governments are choosing not to deflect rocks they could deflect. This framing also fails to engage with the operational reality. DART, the Double Asteroid Redirection Test, flew in 2022 and successfully changed the orbital period of the small moon Dimorphos around the asteroid Didymos. It is the only operational kinetic impactor proof of concept in human history. The mission took years to plan and years to fly. It impacted a target with multi-year warning. For a sub-meter rock detected with 2 hours of warning, like 2022 EB5, there is no deflection option. There is only evacuation, and even that requires the warning to reach civil defense authorities in time, which has happened reliably for every event since 2018 LA. The capability to deflect a Chelyabinsk-class object on a multi-year warning timeline is roughly within reach. The capability to deflect a sub-meter rock on a few-hour timeline does not exist, and likely never will. The physics does not allow it. The third pattern is the framing that Apophis was always going to miss in 2036 and 2068, and that the keyhole closure announcements were a kind of moving the goalpost public relations exercise. The actual mechanism, as I described in Part 4, is radar pings off the asteroid surface during close approaches, processed through orbital propagation through the future flyby geometry. The Farnokia et al. 2021 paper publishes the radar measurements, the orbital fit, and the closure of both keyholes. The paper is reviewed. The data are public. Any astronomer with the relevant orbital mechanics software can reproduce the result. The closure of the keyholes is mathematics applied to measurement. It is not a press release. The fourth pattern, which is the most worth engaging with directly, is the framing that there is no real sunward blind spot and that, if the agencies actually wanted to find these rocks, they could. This framing fails on the physics, not on the politics. A ground-based optical telescope cannot detect a faint moving point against a daytime sky background 10 million times brighter than the night sky. That is not a policy choice. That is the photon arithmetic of how telescopes work. Twilight programs at the Zwicky Transient Facility, at the Blanco Telescope at Cerro Tololo, at Atlas, at Pan-STARRS, push the inner limit of detectability from 60 degrees solar elongation down to 30 degrees. Inside 30 degrees, no ground-based optical telescope can operate. The space-based infrared missions NEO Surveyor and NEO MIR are public, peer-reviewed, instrument-engineered programs. Their published specifications, their orbital plans, and their detection limits are all in the open scientific literature. The reason these missions are still being built and have not flown yet is funding and time, not concealment. They're coming, NEO Surveyor in 2027, NEOMIR in the early 2030s. So the conspiracy framings taken together do not survive contact with the open data. The system is more transparent, not less, than almost any other government operation. The infrastructure of asteroid tracking exists to be public because that is the only way the international warning chain functions. A predicted impactor needs to reach civil defense authorities in 4 different countries within hours. The chain only works if the data are real, the data are public, and the data are trusted. What remains, then, is not a conspiracy. It is a gap. The gap is the sunward blind spot. The gap is the funding and time window before NEO Surveyor flies in September 2027 and NEOMIR flies sometime around 2030. The gap is the fact that a Chelyabinsk-class rock from the sunward direction would, as of today, arrive without warning. There is no political fix for this. The political fight has mostly already been won. NEO Surveyor's funding is locked. The Chips and Science Act prohibits cuts. The launch is scheduled, the hardware is built, the mission will fly. NEOMIR is in early study phase but is on the ESA Space Safety Program list. Both missions will go. There is, however, a temporal fix that has not been won. The gap is roughly 4 to 6 years, from May 2026 to September 2027 for the first reduction in the blind zone, ground-based plus NEO Surveyor at 45 degrees of the Sun. From September 2027 to about 2030 or 2031 for the full closure of the sunward gap when NEOMIR adds in at 30 degrees of the Sun. During those 4 to 6 years, the geometry that produced Chelyabinsk and the geometry that produced the Ohio bolide of March 17, 2026 will remain exactly as it was on those mornings. The rocks do not arrive on a schedule. The mean impact rate of Chelyabinsk-class objects, calibrated by Brown and colleagues from infrasound and satellite detection data, is roughly once every 50 to 100 years. That is a mean rate. The actual events are poisson. The next one could be tomorrow. It could be in 2050. The geometry is what it is. The watch is what it is. So when you look at JH2 on Monday, if you are in a position to look with a 6-inch or larger telescope, or by watching the Virtual Telescope Project livestream that Gianluca Massi will host beginning at 1945 Coordinated Universal Time on May 18th, what you're seeing is the visible kind of asteroid, the kind we catch 8 days out, the kind we describe in advance, with the orbital elements and the closest approach distance and the relative velocity. The kind that gives every news organisation on Earth 2 days to write the close call story. What you are not seeing is the kind that arrives the other way. The kind that comes from inside Earth's orbit. The kind from an Atira on a trajectory that never breaks free of solar glare from our vantage. The kind that, when it finally arrives, lights up the morning sky as a fireball, and the first sound you hear is the rumble 2 minutes later. That rock is out there. The Granvik et al.'s population estimate suggests roughly 1,800 to 2,500 Atira-class asteroids, 150 meters and larger. We have catalogued 40. That ratio is 50 to 1. There are statistically 50 unobserved Atiras for everyone we know. Most are not on impact trajectories. Most will pass close and depart without notice. Some, on long time scales, will not. When NEO Surveyor flies in 2027, the first 1 to 2 years of operations will catalogue huge numbers of these objects for the first time. Some of them will appear on the Sentry list. Some will be high enough on Palermo to merit a press conference. Most will be quiet. The catalogue will finally begin to look the way the catalogue ought to look. Not a list of the rocks that come from the visible direction. A list of all the rocks. Until then, the half of the sky that closed for Chelyabinsk on February 15th, 2013 stays closed. The half of the sky that, on the morning of March 17th this year, dropped a 7-ton air-bursting rock on Ohio without warning, stays closed. The half of the sky that the European Space Agency, in its own words, says we are blind to, stays closed. That is what the news will not tell you about Monday's asteroid flyby. Not that JH2 is dangerous. It is not. Not that the system failed to detect it. It did not. The system worked perfectly. The rock is the size that gives you 8 days. We got our 8 days. We're using them. The Virtual Telescope Project will livestream. Astronomers around the world will turn their scopes on the sky over Leo and watch the bright dot crawl. Amateur astronomers will see it. Children with backyard telescopes will see it. What the news will not tell you is that this is the easy kind. This is the rock we always catch. The rock we don't catch is the one we won't see. The rock we won't see is the one in the half of the sky we're blind to. And that half of the sky is exactly where the last big one came from, and exactly where the next one, whenever it arrives, will come from too. JH2 will pass. Earth will continue around the Sun. The light from Mount Lemon's telescope will catch the next Apollo-class asteroid that wanders into a similar geometry, and we will know about that one too. But somewhere, on an orbit that fits entirely inside Earth's, on a trajectory aimed at a future encounter that nothing on Earth can currently see, a different rock is moving through the daytime sky. It has a name. It has parameters. It has a date. We do not know any of those things yet. We will know when it arrives. That is the question the news did not ask about JH2. That is the answer this video has tried to give, and now you know it too.